Hey everyone, welcome to lesson 1 of theme 3, GCSE Geography. So we're moving on to the juicy stuff now. We've got volcanic eruptions, earthquakes, tsunami, plate tectonics, continental drift. So we're going to get started at the beginning. We're going to look at the theory of continental drift. Where did the idea come from? What's going on inside our Earth that causes continents to drift around? The processes behind it all. So pause the video here a moment, go ahead and write down today's title, and we're going to identify and describe the pattern of how volcanic activity is spread out across the planet. You're going to annotate a diagram of the Earth's interior, and we're also going to explain the concept of convection currents and a new idea called slab pull. So write the title down and we'll get started. Okay, so first off, in the resources that go with this lesson, you've got what's called an anticipation grid. So if you're able to print it out and cut it out, great. If not, then in an ideal world, I'd like you to draw this table into your books. What I'm asking you to do, just to get started, is look at the facts and tick whether you think they're true or false. Do not write anything in the information column. This is just to refresh our memory from year 9 a little bit and see what we sort of already know already. What we already know already? You know what I mean. We're going to circle back to this table at the end then and review the progress that we've made. So read the facts and tick whether you think they are true or false. Some of it might be a guess. That's totally fine at this stage. Okay, so let's get into it. There are 13 main tectonic plates, of which 7 are extremely large. In fact, they've got entire continents sitting on top of them. So the tectonic plate that has North America sitting on it is known as a North American plate. And the idea is that the outer layer of the Earth, it's like the skin on an apple or the shell on an egg. We call it the crust, and the crust is broken into pieces, and we call those pieces tectonic plates. The boundary, the edges of these plates, is known as a plate boundary, or you might hear it called a plate margin. They will use in the exam one or either of those terms interchangeably. They mean the same thing. Okay? So, I think in your handout you've got 2 maps. This one, which shows you the main plate boundaries. North American plate, South American plate, the Nazca plate, the African, the Eurasian, the Pacific, the Indo-Australian, Antarctic, Caribbean, Cocos, and Arabian. These are the main plates. Now, the map on your handout is really tiny. You're welcome to write these names on if you're able to, but you don't have to know them off by heart, so don't stress too much about it. Oh, and the Philippines plate. Oh, and the Scotia plate. You've also got this map. Now, this map shows the distribution of volcanoes and earthquakes, how that activity, that tectonic activity, is spread out around the world. What do you notice from the 2 maps? If we look at this one, and then we look at this one. So the red triangles are volcanic eruptions, and the dots are earthquakes. Is there a link between these 2 maps? Yeah, okay. Pretty much, if there's a plate boundary or a plate margin, that's where the earthquakes and volcanoes tend to be. Now, you do get some what we call intra-plate, within-plate earthquakes. They're much more rare. And this is where, for example, if this plate was coming this way, say, and this plate was coming this way, it's going to squash this plate in the middle and cause pressure within it that might cause the odd earthquake. But on the whole, the majority of volcanic eruptions and earthquakes are distributed. They are spread out along plate boundaries. In particular, there is a really high concentration around the edge of this plate. Look. This is the Pacific plate. So this really high concentration of tectonic activity is known as the Pacific Ring of Fire. You might have heard the phrase before. So what I'd like you to do is pause the video here a moment, stick those 2 maps next to each other, and just write a couple of sentences to explain the link between the 2. Okay, so let's look at why this is the case. Why do earthquakes and volcanoes happen on plate boundaries? What's going on that causes that tectonic activity? Okay, so let's explain the spread, the distribution. So, the idea that the continents are moving has been around for about 200 years, but it wasn't until about 60, 70 years ago that it actually became widely accepted. Now, the first guy to come up with the idea was a German scientist called Alfred Wegener, and he said, people of the scientific world, I reckon the continents are moving. And they were once joined together in one large piece called Pangea, and Pangaea broke up around about 200 million years ago. And since the breakup of Pangaea, the continents have continued to move. They first split into two main continents called Laurasia and Gondwana. So Pangaea broke up around 230 million years ago into these two pieces around 200 million years ago, and it's continued to spread and move ever since into the continental shapes that we see today. And the reason he thought this was happening was because of several clues, pieces of evidence. For example, coal and oil, fossil fuels, when they actually form, you need quite warm, swampy conditions, and yet there's loads of oil under Antarctica and really high quality anthracite coal in the UK. Neither of those places are warm and swampy, that's for sure. So Alfred's idea was that in the past, we must have been nearer the equator, where the climate is more tropical and warm and swampy, and we've since drifted away from the equator to the colder regions of the world that we're in now. The second clue was to do with fossils. So fossils of identical prehistoric creatures have been found in South America and Africa. The fossils of these creatures aren't aquatic. They're not water creatures. They can't swim. The continents are way too far apart, even if they could swim. So how have we got identical species in these two areas of the world? Unless it was all one piece of land and the species lived across the whole area, and then the population got split when the continents split. Final clue, and perhaps one of the strongest ones, is the shape of the continents. Some of them literally look like they used to fit together like pieces of a jigsaw, in particular South America and Africa. So they shouldn't be overlapping, they should just fit along the edge there. So he put forward this idea that the continents are moving, the continents are drifting. And so he called his idea continental drift theory. Now at the time, everyone thought he was crazy. Nobody really believed him because they were like, right, so we see your clues, we accept it kind of makes sense, but if the continents are moving, what's making them move then, Alf? What do you think is going on? And that's the missing piece of the puzzle that he couldn't answer. We didn't have, at the time, in the 50s, when it was kind of really all becoming a major point of discussion, Alfred Wegener didn't have a mechanism for what on earth could be powerful enough to move entire continents. We think we do now, and it's to do with what's inside our Earth's interior. Okay, so that's what we're going to do next. We're going to look at what's inside our Earth. Here's a picture of a cross-section looking inside our planet. As you can see, it's split into 4 layers. The outer layer is the crust. Now this is the thinnest layer. In some places it's as thin as about 6 kilometers, and it varies in depth up to about 70 kilometers. So it's actually pretty precarious, and it's on top of the crust that the continents and oceans sit. Underneath the crust then we've got the mantle. Now the mantle is kind of like melted jam, like a kind of consistency. It's melted molten rock, about 3,000 degrees centigrade. Within that then you've got your outer core and your inner core. The outer core is mostly melted rocks and metals. We think it's about 5,000 degrees centigrade, and then your inner core we think is about the same temperature as the surface of the sun, around about 6,000 degrees centigrade, and we think it's mostly radioactive material and solid metals like nickel and iron. What I'd like you to do, and this bit is a bit tricky, I'd like you to try your best to draw your own version of this cross-section, and on this side of it add some, like, it doesn't have to be super accurate, but add just a couple of lines to represent plate boundaries, and add a label on this side too. I'm going to have to try and write plate boundary with my mouse. Okay. Oh, joined up and everything. Nailed it. Okay, now remember, sometimes they might call it a plate margin, same thing. So basically, take about half a page worth of space in your book, or more if you want, and try your best to make it look just like this slide. Don't stress yourself out with drawing the actual continents and the clouds that are on this satellite image. On this half, just draw plates to represent draw some lines to represent plate boundaries. You could then label where the plate piece is, the piece of crust called a tectonic plate. Whoops. And then put these labels down on this side too. Okay, so pause the video here a moment and do that, please. Okay, so this brings us to the mechanism that Alfred Wegener didn't understand yet that we think is making the plates move. It's called a convection current. Ooh, wrong button. Okay, it's called a convection current. So what we think is happening, now bearing in mind this is all theory, we can't drill into the earth and have a look. Number one, the temperature is too high. Number two, the pressure is too high, and therefore number three, we don't have the equipment. And number four, you wouldn't want to drill through the crust to have a look, because essentially what you'd create is a hole in the crust and the mantle would come spewing out. You've made a volcano. We don't want to do that. So what we think is going on inside, based on all kinds of instrumental readings and what we call extrapolation, kind of expanding our ideas to make guesses, is because we know the mantle is liquid rock and the core is the hottest part of the earth. Of this layer of mantle, where is it going to be hottest? At the top here underneath the crust, or at the bottom here right by the hot core? It's going to be hottest at the bottom here. Now, because it's melted rock, it's liquid, and when you heat a liquid, heated liquid wants to rise. Okay? So it rises away from the core. Now, it can't go through the crust, so it will split here. Okay? Now then, now that it's up here, away from the hot core, its temperature will cool. And if hot liquid wants to rise, cool liquid wants to sink. Okay? And again, it can't cross a boundary into the core, so it will split. Okay? Now that it's back down near the core, it will get heated again, so it will rise again. Okay? And what you have being created here is a current driven by heat. Current means movement, convection means heat, so this is called a convection current. Oh my gosh. New skills being developed today. Convection current. Yeah. Check it. Okay. So, I would like you to add this to your diagram now, because this is the missing piece. When convection currents are going this way, away from each other, underneath the crust, it will pull the crust apart, and you get a constructive plate boundary. Where the convection currents are going this way, towards each other, it will pull the crust on top towards itself, and you get a destructive boundary. So this is what creates either ripping apart or crashing together on the plate boundaries. And the ripping apart or crashing together creates constructive and destructive boundaries, and that's how we get volcanic eruptions, earthquakes, and tsunamis. So add the convection currents to your diagram, and we'll move on. Okay, next thing. Now then, what we realised though was some of the plates, some of the pieces of crust are moving faster than the convection current beneath them. So there's something else going on. It's called slab pull. Have a little look at this video and it will explain the idea of slab pull.
The idea that our planet's continents drift around the globe, periodically glomming together and breaking apart, is at least 200 years old. But most geologists didn't believe it until the 1960s, when mounting evidence made it clear that the Earth's crust is broken up into fragments, and that those fragments, called tectonic plates, are moving. And these days we directly track that motion, with millimeter precision, from space. The common simplified explanation for why tectonic plates are moving is that they're carried along on currents in the upper mantle, the slowly flowing layer of rock just below Earth's crust. Converging currents drive plates into each other, diverging currents pull them apart. This is mostly true. Hot mantle rock rises from the core and moves along under the crust until it grows cool and heavy and sinks back down again. But the plates aren't just passively riding these currents around like a bunch of suitcases at the baggage claim. They can't be, because some of the plates are moving faster than the currents underneath them. For example, the Nazca Plate, a chunk of ocean crust off the west coast of South America, is cruising eastward at about 10 centimeters per year, while the mantle underneath it oozes along at just 5. Neither tectonic plates nor luggage can move faster than the belts they're riding on unless something else is helping to push or pull them along. And some of Earth's plates, it turns out, are pulling themselves. When an ocean plate collides with another ocean plate, or a plate bearing the thick crust of continental land masses, the thinner of the two plates bends and slides under the other. As the edge of the sea floor sinks into the mantle, it pulls on the plate behind it, the same way a chain dangling further and further off a table will eventually start to slide. The bigger the sunken portion of the plate becomes, the harder it pulls and the faster the remaining plate behind it moves. You can find where this is happening just by looking at Google Earth. The incredibly deep, narrow ocean trenches visible off the coasts of some continents and island chains mark the creases formed as ocean crust plunges downward, bending the edge of its neighbor in the process. What's more, these chunks of seafloor are actually helping to drive convection in the mantle beneath them. Sunken slabs of ocean crust block flowing rock from moving further sideways, forcing it to turn downwards and sink. And eventually those slabs get too heavy and break off, plunging slowly toward the core and creating a suction force that pulls mantle material along behind them. So in some ways, seafloor crust is really more like part of the conveyor belt than something riding on top of it. The continents, on the other hand, are baggage.
Okay, so there's gravity at play here. Hey, welcome back. Sorry about that. I had to end up recording this lesson in 2 parts because I pressed escape when I tried to come out of the YouTube video about slab pull, and I forgot that when you press escape it ends the recording, and I didn't want to start the whole thing again, not gonna lie. So I've just made 2 parts. So let's pick it up where we left off. So what I'd like you to do, in your handout you've got a picture of this diagram. Listening to the video at the end of the previous recording for the lesson, that video on YouTube about slab pull, see if you can cut and stick and match the labels to the correct numbers on this diagram. So if you just listen a moment and I'll walk you through. So what we've got happening here, this is a constructive plate boundary where the plates move apart from each other, and this is a destructive plate boundary where the plates crash into each other. It's called destructive because it destroys crust and constructive because it creates crust. So what is happening here, this diagram shows the process of slab pull. Slab pull is basically where the more of this piece of oceanic crust that sinks into the mantle, the more gravity will act on it and pull that slab of oceanic crust down into the mantle. So it speeds up the rate of subduction, the rate of sinking. So the magma rises in the mantle, and what it does is it pushes the crust up slightly underneath the ocean. It's called an oceanic ridge. This piece of plate, this oceanic crust, then moves away from the ridge, and as it does so, it collides with a piece of continental crust, a piece of continental plate. Where they collide, the oceanic crust is forced to sink because it is more dense. That is called subduction. And the friction also drags the edge of this continental crust down a little bit. And what you have forming here is an oceanic trench. We'll come to that later. The more of this that sinks into the mantle, the more gravity takes over and the more it is pulled down into the mantle. So I'd like you to put a subheading, convection and slab pull, cut and stick this image, and then either cut and stick these around it and put arrows pointing to the correct number, or you're welcome to cut and stick them underneath and just write the numbers next to them, or you can always just write the label out if you don't want to cut and stick it. So pause the video here a moment and do that, please. Okay, so you should have them in this order. Let's take a look. Pen. So number 1, the hot magma rises in the mantle. Now magma is the word given to the hot molten rock when it's inside the earth. Once it's been erupted out of a volcano, it's called lava. I don't know why the name changes, it just does. So what then happens at number 2 is the oceanic crust is forced upwards slightly by the rising magma, creating a mid-ocean ridge. At number 3, the crust is moved away from the oceanic ridge by convection currents in the mantle. So you would have a convection current going this way like this. Sorry, I'm sniffing a lot. I've just come in from duty outside and it's freezing today. Okay, so you'd have convection currents doing that. All right. What you then have is the oceanic crust subducts, it pulls the rest of the plate with it, speeding up the rate of subduction, and we've got the sinking oceanic crust drags the edge of the continental crust down with it, forming an ocean trench. So we've got these 2 left for 4 and 5. This one is number 4, and this one is number 5. Okay, so check your answers, make any corrections you need to make. And let's come back around to the anticipation grid we had at the start. So, until 230 million years ago, the continents were joined as one supercontinent. True or false? Yeah, it's true. Pangaea broke up about 230 million years ago, and it made Laurasia and Gondwana land. Gravity causes tectonic plates to move. Partly true. Gravity does move the pieces of crust through slab pull, but it's also convection currents. So write that in the information box. Partly true. Slab pull is through gravity, but there's convection currents going on as well. Planet is split into 4 layers. True. Crust, mantle, outer core and inner core. The outer layer is the thickest layer. False. The outer layer is the thinnest layer, in fact. The thickest layer is the mantle. The mantle is the hottest layer, being up to 5,000 degrees C. False. The core is the hottest layer. The mantle is only about 3,000 degrees centigrade. Pangaea immediately split into 7 continents that we have on Earth today. False. It split first into Gondwana and Laurasia. Convection currents are movement in the mantle caused by intense heating from the core below. True. And the theory of continental drift still hasn't been proven. True. We can't dig into the Earth and have a look. We weren't around 230 million years ago when Pangaea broke up. It's all based on clues that we can see. Today we've pieced together what we think has happened in the past. And that marks the end of lesson 1 of theme 3. Well done. Any questions? Drop me an email as usual, gleasona@hubcymru.net. Otherwise, I'll see you soon for lesson 2.